Hi, everyone. This video presents our latest research. Titled, Rethinking Temporal Fusion with a Unified Gradient Descent View for 3D Semantic Occupancy Prediction. I'll introduce you to GDFusion, a novel method that enhances how we use temporal information in 3D vision systems. This work is particularly impactful for applications like autonomous driving and robotics, where understanding dynamic environments is critical for safety and efficiency. Let's start with the basics. In autonomous driving, a vehicle needs to see and interpret its surroundings in real time. One powerful tool for this is 3D semantic occupancy prediction. Imagine a 3D grid where every small cube or voxel is labeled to show what's there: a car, a pedestrian, a building, or just empty space. This gives the system a detailed map of the environment. But here's the challenge: a single snapshot isn't enough. To make accurate predictions, we need to combine information from multiple frames over time, a process called temporal fusion. Traditional methods focus narrowly on merging voxel data, but they often overlook other valuable clues. Our research changes that by tapping into three underexplored temporal cues: scene level consistency, motion calibration, and geometric complementation. We integrate these into a unified framework called GDFusion. Why does this matter? Think about how you navigate a busy street. You don't just look at what's in front of you right now, you rely on what you've seen seconds ago to anticipate what's next. Similarly, autonomous systems can benefit from memory of past frames to predict the future more accurately. The trick is figuring out how to blend all this temporal data effectively, especially when it comes in different forms. That's where GDFusion shines, using a fresh approach inspired by gradient descent to tie everything together. So, what are these three temporal cues we're working with? Let me break them down. First, scene level cue. This is about the big picture, things like lighting or weather that stay consistent over a few frames. We encode this into the network's parameters, letting the model adapt to the scene's overall context. Second, motion cue. Objects move, and cameras aren't perfect. This cue corrects alignment errors in voxel fusion by tracking motion and refining it with past data. Third, geometry cue. This uses historical 3D information like depth maps to improve how we lift 2D images into 3D space for the current frame. It's a bit like using an old map to fill in gaps on a new one. Each cue adds a unique layer of understanding to the prediction process. How do we bring these cues together? We turn to RNNs, but with a twist. Each cue, scene level, motion, and geometry, comes with its own unique representation. Normally, RNNs struggle with mixed data types. For instance, scene-level cues are encoded as abstract network parameters, motion cues are 3D flow maps, and geometry cues are probabilistic point clouds. These heterogeneous representations vary in structure and scale, posing a significant hurdle for RNNs to handle such diversity efficiently. To address this, we propose GDFusion, a unified framework that reinterprets RNN and updates as gradient descent steps in the feature space. Here's the gist. We design specific loss functions for each cue to measure the discrepancy between current and historical data. For example, scene-level losses focus on global consistency, while motion losses target alignment errors. The gradients from these losses serve as corrections, adjusting the features to incorporate historical information. By applying these corrections, we seamlessly blend scene, motion, and geometry cues into the Visionoc pipeline, ensuring all temporal information works together harmoniously. So, how does GDFusion fit into the Visionoc pipeline? Let me walk you through the practical implementation, highlighting where each temporal fusion step takes place. For voxel-level fusion, to top it off, we optimize this step for efficiency. Instead of storing bulky multi-frame data, we use a single-frame RNN hidden state, slashing memory use while maintaining robust temporal integration. Geometry fusion happens before the 2D to 3D lifting stage. We combine historical geometry, like depth maps from past frames, with current frame predictions using weighted averaging. This enhances the 2D to 3D transformation by providing a richer geometric prior. Motion fusion is positioned just before voxel-level fusion. This step minimizes differences between motion maps across frames. By refining alignment with historical motion data, we ensure past features align accurately with the current frame's coordinate system. Scene-level fusion occurs after voxel-level fusion. Using a self-supervised task, we update network parameters to embed historical scene information like lighting or weather into the current frame's volume features, capturing global context. By strategically placing these fusion steps within the Visionoc pipeline, GDFusion ensures each queue enhances the right stage of the process, delivering both accuracy and efficiency. Let's look at the results on the OCC 3D benchmark using the Nussines dataset. Here's how GDFusion compares to the strong temporal baseline, BEVDETSF, FBOC, and ALOC, as shown in the figure. The results are quite compelling. On the OCC 3D benchmark, GDFusion achieved a 1.4% to 4.8% mu improvement compared to baselines that already incorporated temporal fusion, and importantly, it did so while reducing memory consumption by a significant 27% to 72%. As illustrated in the figure, the memory consumption of traditional method solo fusion scales linearly with the number of stored historical frames, whereas GDFusion maintains memory usage comparable to non-temporal fusion levels. These results highlight GDFusion's ability to deliver superior accuracy with significantly lower resource demands, which are critical for real-world applications. To wrap up, GDFusion redefines temporal fusion for 3D semantic occupancy prediction. By uniting scene level, motion, and geometry cues through a gradient descent lens, we've improved both accuracy and efficiency. Looking forward, we are excited to apply this to other 3D tasks, pushing autonomous systems even further. That brings me to the end of my presentation. Thank you very much for your attention.